Okay, let's dive right into this. Welcome to today's Explainer, where we are stepping into the incredibly fascinating world of trigonometry. Now listen, I know exactly what you might be thinking. For a lot of students tackling the Cambridge 0580 syllabus, trigonometry usually means aggressively punching numbers into a calculator and just hoping for the best. But today, we are going to completely flip that script. Think of yourself as a photographer trying to find the perfect angle. You need to frame your answer to highlight the key evidence. Whether you're taking the 0580, 0606, 4024, 4037, or 4040 exams, we are going to uncover the secret geometry behind those numbers. We'll show you exactly why you don't always need a digital tool to find exact trigonometric values, and more importantly, how to secure every single mark on your paper.
Think about this question for a second. You've probably seen your calculator spit out a perfectly neat number like 0.5 when you type in the sine of 30 degrees. It feels like magic, right? Or just some hidden algorithm. Let me tell you about two students I worked with recently. First, there's Alex. Alex overloads his exam answers with raw mathematical facts, memorizing that 0.5 without any analysis. Then there's Sam. Sam rushes through the paper, completely missing the command word requirements. Both lose crucial marks. That 0.5 isn't an approximation. It's an undeniable geometric truth. Today, we're going to visually deconstruct exactly where that magic number comes from, using nothing but shapes you already know. No rushing, no blind memorization, just pure logical strategy.
We've got a clear roadmap today to get us there. We will cover 1. Beyond the calculator. 2. Deriving exact values. 3. Enter the unit circle. 4. Visualizing trigonometric graphs. And finally, 5. The power of symmetry. All right, let's move right into section 1, beyond the calculator. Here is the foundational secret you need for your exams. While it is absolutely true that most random angles, say 37 degrees or 81 degrees, require a calculator to find their sine, cosine, or tangent, there is an elite group of special angles. These specific angles, 0, 30, 45, 60, and 90 degrees, produce remarkably neat, perfectly exact trigonometric ratios. And the best part? These aren't random. They are derived purely from the most basic, fundamental shapes in geometry. Cambridge examiners absolutely love testing your knowledge of these specific angles because it separates the students who just memorize from the students who truly understand the mechanics of the math. Which brings us to section 2, deriving exact values. What's really interesting here is how we build these exact numbers from those fundamental shapes, using what I call the Peel framework: point, evidence, explanation, link. Let's apply this to 45 degrees. Our point is the exact value. Our evidence is the geometry. Imagine taking a perfect square and cutting it diagonally in half. You get a right-angled isosceles triangle. Let's assign the two equal sides a length of exactly 1 unit. Because it's a right triangle, we can confidently use Pythagoras' theorem. 1 squared plus 1 squared equals 2, so the hypotenuse must be the square root of 2. Now for the explanation. If we want the sine of 45 degrees, which is opposite over hypotenuse, we get 1 over the square root of 2. Rationalize that, and you get exactly root 2 over 2. And the tangent, opposite over adjacent, 1 divided by 1, which is exactly 1. We just proved the math without a single calculator. That's how you link your working back to the command word in the exam question to get full marks. Before we continue with our next proof, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the strategy. This next step brilliantly illustrates our proof for 30 and 60 degrees. This time, we start with a perfect equilateral triangle where every side is 2 units long, and every angle is 60 degrees. Drop a vertical line straight down the middle. You've just bisected it into 2 identical right-angled triangles. The base of our new right triangle is cut in half, so it's 1. The hypotenuse is still 2. Using Pythagoras again, 2 squared minus 1 squared gives us 3, so our vertical height is the square root of 3. Our top angle was bisected, so it's now exactly 30 degrees. Now look at that 30-degree angle. The opposite side is 1, the hypotenuse is 2. Sine is opposite over hypotenuse, 1 over 2. That is exactly 0.5. Mystery solved. This is exactly the kind of deep, analytical thinking Alex misses when he just tries to memorize the final number. So the crucial point here is that all of those geometric steps elegantly consolidate into this incredibly powerful cheat sheet. This table is your new best friend for the 0580 exam. You can see our 0.5 for the sine of 30 degrees right there, our exact root 2 over 2 for 45 degrees, and the unique properties of 0 and 90 degrees. Internalizing this table fundamentally changes how you approach trigonometric problems because you are operating with perfect, unquestionable precision, not messy decimal approximations.
Let's shift our perspective in Section 3, enter the unit circle.
We are taking those static, rigid triangles and placing them onto a dynamic coordinate plane. Welcome to the unit circle. It sounds intimidating, but its definition is beautifully simple. It is just a circle plotted on an XY graph with its center anchored perfectly at the origin, the 0, 0 coordinate. And it has a radius of exactly 1 unit. By placing a hypotenuse of 1 inside this specific circle, we unlock the ability to map absolutely any angle imaginable using a single moving point on its circumference. This is where a student like Sam usually rushes and misses the bigger picture. Don't be like Sam. Take a breath and let's decode how this works.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back to it. Imagine a point, let's call it point P, traveling around the edge of this circle. As it moves counterclockwise from the x-axis, it creates an angle. Because our radius, our hypotenuse, is exactly 1, the math simplifies brilliantly. The sine of the angle, normally opposite over hypotenuse, becomes just the y-coordinate over 1. So the y-coordinate literally is the sine of the angle. By that exact same logic, the x-coordinate represents the cosine. And the tangent, that's simply the y-coordinate divided by the x-coordinate. As point P dynamically traces around the circle, it is continuously drawing out the exact sine and cosine ratios for every possible angle. It's a total game changer.
Okay, moving on to Section 4, visualizing trigonometric graphs.
Let's unroll the unit circle and jump into our interactive workshop. Challenge 1 is the data scan. Imagine we've got 60 seconds on the clock. I want you to extract the core trend here. Think about that y-coordinate on our unit circle. When the angle is 0, the point is flat on the x-axis, so y is 0. As the angle opens to 90 degrees, the point reaches the very top of the circle, so y hits its maximum of 1. At 180 degrees, it's back to 0. At 270 degrees, it hits the bottom of the circle, a minimum of -1. If we plot these y values on a timeline, we get the majestic sine graph. Did you spot the trend? It peaks at 1, drops to -1, has an amplitude of 1, and repeats this perfect endless cycle every 360 degrees.
Now for challenge 2, find the flaw. What about cosine? Remember, cosine tracks the x-coordinate on the unit circle. At 0 degrees, the point is at its furthest right, so x is 1. That means the cosine wave starts its journey at its peak of 1 rather than starting at 0 like the sine wave. But notice how the shape is perfectly identical. If a student wrote that the cosine graph is completely unrelated to the sine graph, that's the flaw. What you should take away from this is that cosine and sine are basically identical twins. The cosine curve is simply a translation of the sine curve, effectively starting its cycle 90 degrees earlier. They share the same amplitude and the exact same 360-degree period. Time for challenge 3, speed writing. You have 30 seconds to write a perfect peel paragraph on the tangent graph. Ready? Go. Tangent is the unique outlier here, wildly breaking the rules. Because tangent is y divided by x, what happens when x is 0? On the unit circle, x is 0 at the very top, at 90 degrees, and the very bottom, at 270 degrees. You literally cannot divide by 0. It's mathematically undefined. This creates invisible vertical barriers on the graph called asymptotes. Because of this, the tangent graph has no maximum or minimum value. It shoots off to infinity in both directions, and it repeats itself much faster with a much shorter period of just 180 degrees. Boom! Full marks for that explanation.
Finally, we reach Section 5, the power of symmetry. Let's see how these repeating wave patterns and circular rotations make calculating much larger angles incredibly predictable. Because the sine wave is perfectly symmetrical, and because the y-coordinates on the left side of the unit circle directly mirror the right side, we get a highly useful geometric truth. An angle and its supplement, subtracting from 180 degrees, will give you the exact same positive y value. This is a massive time saver in exams. Let's look at how this applies in practice. We mathematically proved earlier that the sine of 30 degrees is exactly 0.5. Using our rule of symmetry, we know that the sine of 180 degrees minus 30 degrees must yield the exact same result. And this brilliantly illustrates that if you merely memorize that basic exact value for a small angle like 30 degrees, you automatically know the exact value for an obtuse angle like 150 degrees without ever touching a calculator. It is also exactly 0.5. By the way, students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
Now, cosine operates on a slightly different mirror. Because cosine maps the horizontal x-axis, its positive values mirror each other above and below the x-axis on the unit circle. This means the cosine wave reflects its values perfectly when an angle is subtracted from a full 360-degree rotation. Understanding this rule is like having the examiner's mark scheme right in front of you. Let's apply this. From our exact values table, we know the cosine of 60 degrees is 0.5. Following our symmetry rule, we calculate 360 minus 60, which gives us 300 degrees. This proves that a massive, sweeping angle like 300 degrees shares the exact same positive x-coordinate on the unit circle as a simple 60-degree angle. Therefore, the cosine of 300 degrees is also exactly 0.5. You are literally just recycling the same fundamental geometric truths across the entire circle. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now at @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by.
We have covered incredible ground today, from bisecting triangles to unrolling the infinite waves of the unit circle, all to build out your mathematics success blueprint. We decoded command words, applied the Peel framework, and managed our time matrix. But I want to leave you with one final thought. We just saw positive symmetries, but consider this. The cosine of 50 degrees has the exact same magnitude as the cosine of 130 degrees. But at 130 degrees, it has a negative sign. Why? Because at 130 degrees, we've rotated into the left half of the unit circle where the x-axis is negative. So here is my challenge to you. Pull up a unit circle, grab a pencil, and find one more matching pair on your own. Try exploring where tangent might be symmetric. Mastering these symmetries is the ultimate key to unlocking trigonometry and acing your exams. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.